So we worked through one example there. I've got another 3D moment example here that you can see. We may work through this. I'm going to continue on with Chapter 4. We'll do this kind of as bonus. If we come back to this, perfect, if we have time. But I don't want to overload us. I want to kind of make that an optional extra video. Unless I just really blaze through these really fast. So there's other stuff we really need to make sure we cover out of Chapter 4. A single 3D example is good. 2 would be great. But let's talk through the rest of the content of Chapter 4 before we work another 3D example. Within Chapter 4 is this concept of the couple moment. The couple moment is a moment produced by two equal and opposite forces. Very simple. If I have force F and I have some perpendicular distance D, and that distance D is to the line of action of an equal and opposite negative F. That would be the same. I could replace, if I've got two forces that are equal and opposite and a certain distance apart D, they're parallel and they're distance apart D, I could replace that with a moment. Now notice these guys are causing a clockwise moment the way they're drawn. So these are going to generate a clockwise moment, and the magnitude of that moment is going to be force times distance. Now why is it just one force? Well, if you look at it this way, if I put my pin right here and I apply my force basically in the direction of that, you can see it's going to cause a clockwise rotation. Now, what is the moment caused by this force? If I put my pin right here, the moment caused by this opposite force is going to be 0 because it passes through that point of rotation. Hence the reason it's only one force. The other one gets canceled out, so to speak. And also, the thing is if I'm drawing a free body diagram and I've got two forces equal and opposite, a set distance apart, you can actually remove them if you like off the free body diagram because they have no net effect. The sum of these two forces is going to be 0. However, you do have to replace it. If you remove these, if you cancel these out, so to speak, you do have to replace it with the moment caused by, or the potential rotation caused by those two forces. So this is kind of a common thing that you will encounter. What does this mean? Well, I mean, if we do just a really, really simple example of this. Let's say that I've got, I don't know, some beam here where I've got 20 pounds and I've got 20 pounds and they're separated and they're both vertical and they're separated by a horizontal distance of 2 feet. Well, what we're saying is that, if you look at this thing, it's just going to spin. Right? If I just add a beam and I apply a force here and a force here, it's just going to spin. And as long as I apply the same amount of force here as I apply here, right? If I apply them right in line with each other, notice I can apply the same amount of force and the pin doesn't move. But if I apply them off-centered, the pin may not move, but I can get it to rotate. And that's what we're saying here. If I apply these two forces, if I apply them right together in the same line of action, this thing is in equilibrium. No, it's not doing anything. But because I'm applying them off-center, it's going to rotate. It's not going to move up or down. It's not going to move left or right because there's no X force applied. It's not going to move up or down because these two are going to sum up to be 0. However, just because it doesn't move, now we're in statics, just because it doesn't move linearly doesn't mean it couldn't potentially rotate. In a dynamics course, we would talk about, okay, well, what's the geometry and the shape of this thing? How fast is it going to begin rotating by applying these two forces to it? In a statics course, we're just going to be looking at, well, what is the total moment and how much moment is required or what forces are required to keep this thing from moving. That's going to be the later chapter. So we could replace this and it's going to be 40. It's going to be 40 pound-feet, 20 times 2. Right? Remember up here, it's just one of the forces because one of the forces basically is passing through the point of rotation. The other one is set distance d away. So one of these forces is 2 feet away at 20 pounds. That's generating a 40 pound-foot moment that if we don't constrain it, if we don't do something to keep this static, that will cause a counterclockwise rotation by applying these two forces. Okay. Now, the thing about a couple moment is I can apply that anywhere on that diagram. Anywhere. That couple moment has no specific location. We get to chapter 7, we talk about shear moment diagrams. We might need to worry about the location, but up until that point, we can apply this anywhere along the beam, and mathematically we're looking at the same quantity. Okay, so a couple moment doesn't matter where we put it, but the forces though, it is very important where I place forces on my diagram, and that's the whole point of the last little bit of chapter 4 is where we introduce this concept of equivalent force systems. Equivalent force systems. What does this mean? Well, so equivalent force systems means that, so here's the concept, right? If I've got this beam here, some member AB, and if I apply a force F along the long axis of this beam, well, here's the thing. I can apply that force anywhere along its action, anywhere along its line of action. So I can apply it right here in the middle. Force F along this member AB. I can apply it all the way at the end. Apply it all the way out here. Now, if these are all the same, these will have the same effect. Moving a force along its line of action has no effect. However,